All right, so we're going to talk about the Taylor and Maclaurin series, and then the theory behind it, and then how to find a Maclaurin series, and then how to find a Taylor series. So first off, what is going on here? So a Taylor series of F at C, okay? Sometimes they say centered at C. Okay, sometimes it says centered at C here. What is this? If F has a power series representation at C, that is, what does that mean? That means if f of x is equal to n equals 0 to infinity, an x minus c to the n for x minus c less than the radius of convergence r, then what happens? The nth derivative of the function f evaluated at c exists for every positive integer n, and the ANs are defined to be f nth derivative of f evaluated at c divided by n factorial. Okay, so that tells me this: the Taylor series of f centered at c, this is f of x equals, and you need to have this memorized, n equals 0 to infinity, fn evaluated at c over n factorial, that's my a sub n term, x minus c to an n. So this is a special power series, okay, where the coefficients are found by taking the nth derivative, evaluating it where the function is centered, and then dividing by n factorial. That's the ANs there. Okay, it's a power series with special coefficients. So what is this equal to? This is equal to f of c plus f prime of c f prime of c multiplied by x minus c plus f double prime of c over 2 times x minus c squared plus f triple prime of c over not 3 but 3 times 2, which is 6, times x minus c cubed, and so on forever and ever. Okay? Now, there's a special case here that has its own name, special case, when c is equal to 0. So when we're centered at 0, f of x becomes a series n equals 0 to infinity of f, the nth derivative evaluated at 0 of n factorial times x to the n. This is the Maclaurin series. The Maclaurin series of f of x. Maclaurin series is a special case of the Taylor series. Taylor series is the most general case, right? Maclaurin series is whenever c here is equal to 0. It's a power series in 0. Okay? So that's the theory. Let's show you the application here, how this is used. So let's start with the easier one, the Maclaurin series. So I want to find the Maclaurin series of the function f of x equals e to the x and the radius of convergence. Okay, so how do I do this? Well, I use my formula that I just came up with. Okay, I use the formula that I just came up with. All right, to get my ANs, I need to take the derivative, evaluate the derivative at 0, and divide by n factorial. Okay, so start with the first one. When n equals 0, that's the 0 derivative, evaluated at 0, so that's just f of 0. Okay, so if f of x, let's get out of that. Come on. If f of x is e to the x, and f of 0 is e to the 0, which is 1. Okay? Now, f1 of 0, this is f prime of 0. So what's the derivative of e to the x? The derivative of e to the x is e to the x. That makes it easy. So this is e to the 0, which is 1 again. What's the derivative of the derivative? That's the second derivative, evaluated at 0. Well, guess what? The derivative of e to the x is still e to the x. Evaluate that at 0, it's still 1. So what's happening? As I go on and on and on forever, this one's pretty easy. The nth derivative, evaluated at 0, that's equal to e to the 0, which is equal to 1. Okay, so no big deal there. This numerator part is just 1. So this becomes 1 over, and then what do I have? N factorial, okay? And then what is it? The second part is x to the n. Since it's a Maclaurin series, it's x minus 0 to the n, which is x to the n. That's why we just have the x to the n there. Maclaurin series is centered at c equal to 0. Okay, so what do I have here? This is the series n equals 0 to infinity of fn evaluated at c, which is 0 for the Maclaurin, over n factorial x to the n. We determined that fn of 0 is 1, so this is n factorial in the denominator and then x to the n here. Okay, so simplified here, what is this? This is like series n equals 0 to infinity, x to the n over n factorial. Now, that is my e to the x, right? This is my e to the x function. I need to figure out the radius of convergence so I know what all x values this is actually equal to e to the x, okay? Because maybe it works, it converges for some and it doesn't converge for other values of x. But that's a pretty interesting fact that I can have this simple e to the x function, which is a transcendental function, e to the x, right? And that function can be written in terms of polynomial, okay? So pretty interesting fact going on there. But besides the point, let's run the ratio test. So the limit as n goes to infinity of an plus 1 over an. So what is this? This is a limit as n goes to infinity of what? X to the n plus 1 divided by n plus 1 factorial all over x to the n divided by n factorial. Keep, change, flip. Limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times change to multiplication, flip the denominator, becomes n factorial over x to the n. Okay, so this is equal to the limit as n goes to infinity. Now the x to the n plus 1 and x to the n cancel, and what do I get? I get x to the 1. Now the n factorial and the n plus 1 factorial, that's n plus 1 times n minus 1 3, 2, 1, right? So this n minus 1 all the way in the dots cancels with that n factorial, and so I'm just left with n plus 1 in the denominator there, okay? Now, when I take the limit as n goes to infinity, I don't care about the x. I can pull it out. I can treat it like a constant. And I take the limit as n goes to infinity of 1 over n plus 1, which I know this thing heads to 0. So I have something times 0. And when is that going to be less than 1? This is true always. Because when I multiply a number by 0, I get 0. So that's always going to be less than 1. Okay? So 0 is always less than 1. So what does that tell me? By the ratio test, the series n equals 0 to infinity, x to the n over n factorial converges for all x and has radius of convergence equal to infinity. Okay? So my radius of convergence is equal to infinity there. All right? So this is an amazing fact that says if I want to approximate e to the x, and I don't know how to do e to the x by hand, all I need to do is write out some terms here. So n equals 0, that's x to the 0 over 0 factorial, plus x to the 1 over 1 factorial, plus x to the 2 over 2 factorial, plus x to the 3 over 3 factorial, and so on, right? So what is this equal to? Well, 0 factorial is 1, and x to the 0 is 1. So that's just 1, plus x squared over 2, plus x cubed over what's 3 factorial? That's 3 times 2 times 1, which is 6, and then so on and so on. So depending on how close you want to get to the real answer e to the x is how far you go out in your terms for your series. You know, if you go out to infinity, if you go as n goes to infinity here, then you're going to get exactly equal to e to the x. But if you stop at some point, which you got to stop at some point if you're a person or a computer, right? Then there's going to be some error involved. Okay, so but you can make the error as small as you need to make it to where you're still accurate to hit your target. Okay, pretty interesting idea. We'll dive more into when we talk about the nth degree Taylor polynomial. Okay, but let's do one more where we have a Taylor series. Okay, so a Taylor series, so I want to find the Taylor series for f of x equal e to the 3x. So instead of e to the x, I got e to the 3x centered at pi. So now we're centered at pi. This is what makes it not a Maclaurin because I'm no longer centered at 0. So I'm centered at pi here. So let's write out our definition. First thing I want you to do is write out the definition. 0 to infinity. Fn of c over n factorial x minus c to the n. What can I start plugging in here? Well, right off the bat, what do I know? I need to know, my c. My c here is pi. Okay, so the nth derivative evaluated at pi over n factorial x minus pi to the n. Okay, so truly the only thing I need to figure out is this piece right here, and then I've got my Taylor polynomial. So how do I do this? I'm going to give you my method of doing this. So so I've got my n for my first part of my table. Okay, I'm going to have my function with the nth derivative for the second part, and then I'm going to evaluate my nth derivative at the c value. Okay, and for this particular one, my c is equal to pi. So at 0, that's f of x. What is f of x? That's e to the 3x. Okay, so f of pi is e to the 3 pi. That's the first one. The next one at 1, that's the first derivative, which is chain rule. E to the 3x is 3 e to the 3x. Okay, So this is f prime of pi, which is equal to 3 e to the 3 pi. Okay. The next one, the second derivative, okay, same thing here. I have the constant out front, but now the exponent, the chain rule gives me another 3 factor, so I have 3 squared e to the 3x, right? So that's 3 times 3 is 9, right? So that's f double prime. There's a reason I'm not writing out 9 here. Hopefully you're going to see a pattern here, okay? The 3 here, once you figure out your pattern, once you figure out the pattern, then you don't have to keep doing this, okay? Once you figure out what the pattern is, then you can write out the nth term, right? So I think you probably see a pattern now, dot, 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 all the way down to n. So if I'm going to do the nth derivative, well, what do I notice here? I notice the third derivative gives me an exponent of 3 here. The second derivative gives me the exponent of 2 here. The first derivative gives me the exponent of 1 there, right? So I see a pattern developing. It's 3 to the how many derivatives I've taken. And then what do we see that's the same every time? Well, e to the 3x is the same each time, so I'm just going to write e to the 3x there, right? So if I have the nth derivative evaluated at pi, I replace x with pi. And so this is 3 to the n, e to the 3 pi. Okay, e to the 3 pi. So this right here is what I'm trying to get right here. So what is my answer? This is the series n equals 0 to infinity, 3 to the n, e to the 3 pi over n factorial x minus pi to the n, okay? So when I look at this, I see I've got this is a series in terms of n, but I've got this constant here, so I can pull the constant out if I want to make it all clean and nice. E to the 3 pi, and then my series n equals 0 to infinity, 3 to the n over n factorial, x minus pi raised to the n, okay? This is the Taylor series of f of x. Okay, so that's the Taylor series of f of x. Let me copy this and write it down here. Which is equal to e to the 3x centered at pi. Okay? Pretty cool. I hope that you figured out, and maybe you'll use my table method when trying to figure out the nth term. Because the nth term, that's really the hardest part of this problem. Really, once you figure out the nth term, then you basically got it, okay? Because the n factorial stays the same, and then the x minus c raised to the n, that's always the same too. Okay, guys, good luck.